Good morning, good afternoon, or good evening from wherever you are. I'm Ed Kohler with Avaya, and I'm here to talk with you again about microsegmentation. But this time, I want to talk about the details of designing an appropriate microsegmented environment for the IoT. On the last video, we talked about microsegmentation and how it can be used in concert with stealth technologies to provide for a secure IoT framework. But there are a number of questions that went unanswered, and some that may not have even occurred to you. We're going to go through some of those today. How do you identify what systems need to be within the footprint? How do you identify which systems should be protected? We're going to talk about that in part one. Part two will focus more on the aspects of securing the microsegmented environment once it's designed. How do you identify who touches what, when, and where, and allowing access for those different microsegments within your environment? Because obviously, if we design the microsegmented environment, it's all for naught and provides very little value if we're not mandating the control and access of who touches what, when, and where in the microsegmentation design. So, without ado, let's step forward. And the best place to start is to put on the hat of our enemies. When we look at an attacker and they're trying to gain access to your network, there are a series of steps that are typically used. And keep in mind that this is, we're showing an individual here, but I want to emphasize, as we pointed out in the previous video, these are whole IT organizations. Many times companies, dark organizations, many times whole nations will sponsor these efforts. And this can be for a series of purposes, either political, commercial, whatever the case may be. But the point is that it could be an individual or it could be a group of individuals that go through these phases. Now, the first step is actually gathering information. And this is where the attacker will typically start to gain some knowledge of exactly what you're about. And this includes topology discoveries, getting as much visibility into the network as possible, the ability to use target information on DNS resources in order to establish signatures of footprint. And there are many tools out there. Nmap is a great tool, EtherApe if they're local to your access. Tools like that to give large amounts of information to someone who is just at the information gathering phase. The other aspect, though, is looking at web services. If you're an e-commerce site, you probably have several exposed web services for your customers. Analyzing exactly how those are architected, what sort of exposures to the database are there, realizing that there's several methods that can be used through the database to gain access to the system OSs. So all of this becomes multifaceted, and it starts to develop some sort of signature of a strategy here. But I also want to talk about this last bullet, which is the physical aspect, shoulder surfing, which is people just coming through, overlooking the someone's shoulder while they're typing a password, or perhaps listening over a cubicle wall to a conversation, things of that nature. There is also the ignominious dumpster diving, which is still prevalent today. You will be shocked at the amount of people that throw away information that is confidential, totally intact, with no consideration to proper disposal according to policy. But also, let's not forget about office diving and conference room diving. And what do I mean by that? How often do you bring people into your building and have them sit in someone's office before they come back from a meeting? And perhaps on their desk, there may be certain pieces of information, that the individual could perhaps either photograph or very quickly read. In a conference room, how often do you have someone come into a conference room and perhaps there's confidential information on the whiteboard that they can take a quick snapshot of or make a mental note of prior to other individuals coming in? So make considerations to that as well. And then also there is the gray area of social engineering. Why do I say it's a gray area? Well, it can be embodied in a cyber sense or a physical sense. And in the cyber sense, it's obviously email and phishing and things of that nature. But then also there is the the ability to use social engineering with just regular social tools such as Facebook or LinkedIn or any of the other tools that are out there. Now, The other spectrum to, social engineering is physical, purely physical. Imagine, you're meeting with a friend for lunch, and he was a colleague of yours, but he has since moved to another organization, and that organization is a competitor of yours, and he does not tell you. So he hasn't volunteered the information to you, but you start divulging information and updates to him, and he just silently listens as you tell him this information. That's a great example of how something like that can happen. And the other individual can walk away with even a moral aspect to say, hey, I didn't ask him any of that information. He just volunteered it to me. So there's that type of channel exchange as well, which we can do very, very easy, particularly in today's industries where people are so mobile across different vendors and different companies. And then finally, the other aspect is just the simple phone call, calling you saying they're from the IT department and they may know your username and they may know certain other aspects of information that gives them some degree of authentication or authority, and you start volunteering certain information that perhaps you shouldn't have divulged. So there's several ways that this physical venue can take place. But in this phase one, it's all about really gathering information to what you're all about. Now, once they've gathered that information, the next thing they're going to do is they're going to go through and look and identify vulnerabilities. And this is actually looking at operating systems, database types, things of that nature. And then there will be a series of tools that will be selected. And here we're starting to see a strategy unfold where they're saying, okay, now I know the systems, I see what I see, and now I know the vulnerabilities that I can leverage. Now some sort of strategy occurs for the actual exploitation. And we list three here: pure denial of service, or perhaps a distributed denial of service, or remote exploits, i.e. payloads, malware, things of that nature. And then this third category, the advanced evasion techniques, where payloads are actually divided up and morphed into fairly innocent looking data sets, and they're injected into the system. They will sit for a period of time until an application call or a certain time of day or date, or even a phone home from the creator of the code, and next thing you know, the payload becomes intact and goes active. Now, after, there is always the post-exploitation, and keep in mind that this could be after the attack, but it's also something intermediate too. Once they've gained access to a system, or once an attacker's gained access to a system, they typically want to have a way to get back in. And this is the installation of reverse shells to provide for backdoors of access, the ability to use AET type code to provide persistence. So if something comes like a malware detection and finds the runtime code and removes it, the AET can always reinvoke itself to life at a further point in time. And then finally, the other aspect is anti-forensics. This can perhaps be the manipulation of timestamps, obviously code removal for anything I've used transiently. I might do data set removal as well. There also could be the aspect of user account removal, not only the accounts that the attacker created in the process of his attack or her attack, but also perhaps other user accounts, valid users in the organization that may have been used in the attack to brush all trails. Then the final thing is total system crash, just taking the thing and crashing it. But more and more prevalently, we're starting to see folks going in and not only running the attack, taking the information, but then encrypting it all and then holding it all for ransom. So given this, we see that this can be a multi-step environment. You have an initial access. You have the attacker. Once they gain the information that they look for, they start looking for the vulnerabilities. And this basically gets to east-west movement, lateral movement through the systems and groups of visibility that they can see. Because remember, they discovered these systems through their information phase in step one. And once they discover a vulnerability and they have a vulnerability ID, they run their exploitation, and they will do a privilege escalation, and that provides north vertical movement. What do we mean by north movement? North is the target. And if it's a PCI domain, it's credit card data. If it's a HIPAA environment, it's healthcare records. North is the target. This is the privilege escalation. This gets them further inbound into the network. Now, in a flat network architecture, this can be relatively quick. Once they do their initial east-west movement, they pass the demarcation for security. Now they're kind of the fox in the chicken coop, and if they have system visibility, the attack is very, very quick. Other segmented environments, it may require multiple steps, but remember, IP topologies allow for the next step now. Now the attacker will use the same east-west movement, the same discovery techniques to go further and further into the network information. And remember, the more information they gather, the more knowledge they gather about your infrastructure, the more their strategy is going to be optimized as they move forward. So micro-segmentation is really a good thing. Micro-segmentation limits east-west movement. And stealth, the ability to use technology other than IP to move data, limits network visibility. So we provide a very strong microsegment environment that's dark. This really leads to a very good security practice. It also leads itself to a very well-defined audit and data footprint documentation practice, because obviously if you've designed the microsegment, you know the systems involved in the confidential data footprint. Also realize that now you can kind of relook at the way you're handling your demarcations. And in this example, I've got guests and contractors in a totally separate environment with indirect relationship or perhaps no direct relationship to my true internal threat risks. And then also note that I also have the internal threat, which is again tiered with high-grade segmentation so that the green and blue domains are in essence not available to the internal threat. And stealth technologies provides and mitigates the discovery of those resources even existing. So we take away a lot of the rungs in the ladder and we limit attackers' visibility, thereby frustrating both external and internal threats. Now, really, when we get down to this, that's all well and good, as I said earlier, in knowing the systems and going along Security 101, that only the systems that need to know should know. That's all well and good, but we still have to really tackle the fact that we need to validate where the private data exists. And this is the ugly truth in microsegmentation. There is no magic wizard that you can buy off the internet that you can run against your organization and say, oh, here's my confidential data. You have to go through some work, and you have to develop the trace processes and the systems to document the footprint and to develop the diagrams and everything else to show the interacting systems and how the private data moves. Once you do that, then you can go ahead and start designing your networks. But also realize that once you're done, you're still not done. You have to develop penetration test methods. You have to go ahead and do ongoing evaluation of these threats, vulnerabilities, and risks against the microsegmentation environment. Now, the real value that we bring to the table with SDN Fx is that in a private data footprint, the more engineering you will require for the more technologies you have. And that makes a lot of sense. With us, with SDN Fx, you can significantly reduce or eliminate other technologies, which means we can in turn eliminate access control lists and route policies. We also allow for the vast reconsideration of the way you're doing your security demarcations, and that is quickly highlighted on the previous slide. We also need to consider authentication and authorization into the network, and we're going to talk about that in part 2, controlling users and things of that nature, but more importantly in the IoT environment, controlling devices, device types, and their roles, and making sure that they're put into the appropriate microsegment for proper operation. And then finally, the management applications. Let's not forget that. If you can manage devices within the secure private data environment, then that device, that particular element that can manage those devices is actually part of the secure data footprint. Great example is a network switch. If I can log into a switch and I can make changes to that environment and modify the confidential data footprint, then guess what? That switch is part of the confidential data domain. Consequently, if I have an IoT technician and he's sitting in his home and he's VPNing in to change that switch, that VPN connection and his PC in his remote residence is part of the confidential data domain. Now, the next question is, how do I decide how to design a stealth network architecture? And obviously, the stealth service should match the confidential data footprint. But again, that can only be established by knowing the range of the data and the systems that interact with it. And it really means one thing: data discovery. Now, data discovery has a nasty reputation as being a dark art, and to some degree it is. I'm hoping that I'm going to give you some insight as far as how you can proceed, because there are some well-understood methodologies that you can use. And there's also a few little cheats that I want to go through as well, which will kind of escalate in the learning process. Because at the end of the day, if you really can't get this information down, you really can't design a microsegment environment to secure the data domain you're looking to protect. Now, fortunately, there are a few predominant patterns that exist, and I want to talk about that before we move forward. They really come in three forms. There is the linear, the multilinear, and the looped. A great example of a linear, which is the simplest, is a PCI cardholder domain. You know, you have a point of sale system, it takes the credit card transaction, puts it up to a data center DMARC and off to a financial partner, and that's pretty much the footprint. Very few people or companies will store credit card data. And obviously, if you do, then you're into these other data footprints. Now, the second example is a multilinear or a meshed footprint. A great example is video surveillance. And keep in mind that this could be either a unicast or a multicast implementation of video surveillance. Why do I say that? Well, keep in mind that you might have a video surveillance camera. It's most probably sending a video feed 100% of the time to a digital video recorder. But you can also bet that close to 100% of the time, you've also got some sort of security guard watching it as well. Now, if you take dozens of these cameras and match them against dozens of DVRs and perhaps dozens of security desks, you start to see a very strong mesh signature to the way the data footprint operates. This is exactly why we say it's a great example of a multilinear meshed footprint. The final example is a multi-tiered looped footprint. And the reason why we say that is this is typically a signature of automated systems and system elements that need to have isolated communication domains, interaction tiers, if you will. A great example are sensors and controllers interacting with higher level flow coordination managers. And we'll actually use that as an example when we look at the looped footprint at a closer level. Now, the good news here is about 90% of the interaction that you're going to find in the industry fits into one of these categories. The bad news is that these may or may not be mutually exclusive. In other words, you may find them within a single secure data domain. Now, what do I mean by that? Well, we could have a multilinear footprint example, of video surveillance, and you could have a simple looped process. A great example is, a camera seeing something going on, judging it as a threat, and sending out an alert. That's going to create a process loop. That's a great example of that. Now, the good news at the end of it all, though, is we can really boil it down to a series of steps so that you can kind of establish, with appropriate systems exchange and knowledge and talking to the right experts who have provided either the products or the system design that you're looking to secure, you can actually boil down the signature of the data footprint you are actually working with. Now, before we go and talk about these steps, let's look a little bit closer at each of these, and it's important. In the linear example, we typically see a unidirectional data flow, or it could be bidirectional, but keep in mind it is linear. It is point to point between, a client to a server, for example, or a sensor to a controller. These linear data footprints are typically fairly easy to document. They're very consistent in the way they behave. And PCI is a great example of that. We see our point of sale interaction moving up to the PCI application. We hit a demarcation to a financial partner, and then probably the transaction is flushed and probably deducted even at the point of transmission. Now, this is very simple, easy to document. Notice how it can be handled atomically with an L3 or an L2 VSN. For example, we have many customers that utilize a single L3 VSN or a series of them for PCI domains. And then we have others that use L2 VSNs and collapse them up to the security demarcation and terminate the stealth L2 VSNs that way. Either design is valid. Either design provides a very clean demarcation to a linear data footprint, which is incredibly easy to normalize and fairly easy to document. In the meshed example, or multilinear, we see that things are a little bit more complex. But they're still linear at the core. We have the camera to the security console, the camera to the digital video recorder. We also see, however, that these can be systemic tree. This could be multicast based or IP multicast based, and this is becoming increasingly prevalent in the video surveillance arena. We also see that there could be secure connections to external organizations. So the mesh could be extended out across the security demarcation, so either a security agency or perhaps a police or something of that nature can actually receive the feeds from the physical perimeter. And these are a little bit more difficult to normalize from an environment perspective because you really have to catch all of the flows in order to really normalize how the data occurs in normalized flows across the network infrastructure. And keep in mind that with IoT and the ability for automation, this can be made more complex. And this is a great example here, a loop data footprint within the meshed architecture. A great example of this is we have a video surveillance camera that's looking at a fence perimeter. It sees someone climbing over a fence. So it sends out a security alert. That security alert obviously alerts the folks at the security console. The digital video recorder has it full time, but perhaps now is passing it over to analytics. We also have an exterior alert that's going out across the security demarcation to the external security organization, whether it be the security agency or perhaps police. Also, the security alert could cause the locking of entry and exit in the particular zone of the area of the intruder. Note how we have a series of chains of events that are occurring in the physical worlds as a result to that individual hopping over the fence. We're going to come back to this in a later point because it's an important consideration that you're going to see more and more in the world of automated IoT frameworks. The third and most complex example is shown here, and this is a true automation loop. This is where we have a requirement for operation tiers, or what we call interaction tiers within the IoT framework. Now I want to bring your attention up to the upper right-hand portion of the slide. We see that we have a control master, and that obviously is running some sort of algorithmic process to provide an optimized operation of the physical environment down below, which is basically the fluid levels. Now we see that we have several components that are providing information to or action from the master controller. Let's talk about the sensors first. We have S1. S1 on the far left-hand side is reading the fluid level of the reservoir or the tank. It could be chemicals within an automated production facility, could be a water level in a reservoir for a dam, for instance. We also have S2, which is moving in towards the center, and that's providing an actual state feedback of the gateway or valve. Is it 30% open? Is it 30 centimeters open? Or perhaps it's providing the information from a flow perspective, from a gallons per second. In either way, we're able to monitor the actual state of the physical constriction element. And then the physical constriction element itself is managed by the programmable logic controller, which again is receiving control from the control master. Note how the algorithm is taking in consideration of feedback from S1 and S2 in order to actuate the control of the PLC, which will in turn determine the state of the gateway or valve. It's a complete feedback system which allows the system to normalize and optimize itself as it moves forward throughout its process. Note how these environments really will only work properly if they're isolated from one another. And this really gets back to this concept of a tiered VSN, not only for the aspect of isolation and control of the data flows, but also for aspects of security as well. There's no way that I can really interfere between these certain flows without actually getting membership and into the actual micro segments themselves. So we see that S1 and S2 have their own dedicated L2 VSNs, and these have dedicated connections to the master controller. We also see that the master controller has a dedicated connection down to a control L2 VSN, and the only members of that environment are the programmable logic controllers. There is no way for S1 and S2 to communicate. And these can become very, very atomic. For instance, you could have, PLC 1 to master controller 1 and PLC 2 to master controller 2. These can become very atomic one-to-one relationships if desired. The service densities within SDN Fx provides a service density of 16 million service entries. So we have more than enough atomic service entries to provide whatever degree of tiered isolation is required within the IoT frameworks. Now, looking at these three footprints, we can kind of see that we can deal with signatures here once we can identify how data is moving. So this is a well-accepted 10-step process, or actually it's a boiled-down process of 10 steps. The first thing that you want to look at is what is creating the data. You need to establish a starting point. You have to find out where the data is coming from. Many times that's going to come from a systems expert, and many times it's incredibly obvious, such as a point-of-sale system for PCI. However, in the looped example, we saw that determining a start to the framework is difficult. You really need someone with systems expertise that's going to be able to give you that kind of guidance. The next thing you want to look at is what is the method of transmission? Is it TCP? Is it UDP? Connection to connectionless? Is it multicast? Is it encrypted? What is the protocol? Is it even IP? Also, what are the application protocols being used? All of this will give you some idea of the signature and actual method of relationship between these points, because the next thing you're going to look at is if you're sending data, there has to be something receiving it. And if it is receiving the data, does it store it? If so, how and where? And what systems are using the data? And that kind of gets into a plural context. And that, again, gets back to a video surveillance camera sending video to a DVR into perhaps 2 or 3 security consoles. What are they using it for? And this is key, understanding the actual application that you're looking to secure. What are these systems using this data for? Is it metrics in the case of S1 and S2 coming to the master controller? Is it control coming from the master controller down to the PLC? Understand exactly what is going on between these actual composite elements. And then finally, we start to look at do the systems generate emergent data? And I often get weird looks when I use that term. What do I mean by emergent data? I mean data points that simply have not existed prior to the communication data flow, or more properly termed, the compute data flow. Realize that at each point of interaction, something may compute, and something may run an algorithm against that data set and come up with a new pertinent value. A great example is S1. S1 is monitoring the level of the reservoir and constantly feeding that information to the master controller. That's emergent data. That's data that did not exist prior to the loop process flow. S1 is providing that level, and then S2 is providing emergent data on the state of the gate. And every time the gate changes, there is emergent data that will be generated to show the change of the controlled environment. This is all what I mean by emergent data. But also realize that emergent data could be used for algorithmic processing. Data analytics is a very good term. If you've ever done long division or even simple addition, you'll know that you come across several numbers that you use throughout your calculation that you, in essence, throw away. You don't use them at the end. You come up with your answer. But the data that you created, that emergent data, was important in you arriving at your end answer. Obviously, if these happen in simple mathematical computations, imagine what happens in a true analytics process. You have boatloads of emergent data that is created through this process called shuffling, which moves from east to west across the top of rack environment. And these emergent data sets are used for these higher level computations. So, whatever type of analysis you're doing, that is very, very common. Now, quite frankly, many times this information will not be confidential. For instance, if I pull up the value of 1.957 and have no context to what that means or how it's used within the context of the analytic process, then what value does it have? But you really have to look at that. And also, if the emergent data is being created, you have to say, well, is that data then sent somewhere, or is it stored, or is it used? What do I mean by that? Well, obviously, if it's sent somewhere, it could be sent to be stored. It could be sent to be used, or the element that's generating the data could be using it to tune itself, to modify its behaviors. If the answer to that is yes, then you have to say, well, is that data confidential or critical? Most probably, if what you've done up till now is critical, then this probably is too, because this is actually giving you the result or influencing everything that's gone on up until this point, and it could very well be a looped data footprint. If the answer to that is yes, then 10 takes you back to step number 1. You are now looking at another data point that is actually creating confidential data, and you need to now go through the next steps in order to identify that. And at that point, you're very probably in a looped or an automation type framework where you have several systems that are interacting against the data feeds working within the confidential data footprint. Now, this can all be done, obviously, in a very detailed fashion on your own. If you're really good with a sniffer and you're a real good detective and you got a boatload of time and a boatload of resources. But quite frankly, that's a very, very tough road and a very, very difficult path in order to identify exactly what you need to secure. By far, the better way to start is to go and talk to the subject matter experts. Talk to the ones that actually work with the application or designed it. In the case of the PCI, talk to the people that implement it. Perhaps even talk to the vendor of the PCI point-of-sale systems. Same thing with medical equipment. Same thing with automation design. And then I have this other category called risk assessment. What do I mean by that? Well, let's realize that, up until now we've talked about the IoT and a lot of devices communicating and exchanging information, but realize we still have a lot of information that we might be judging as confidential assets or intellectual property. Great example of that is, for instance, with oil and gas, certain geologic information that I might be pulling from a region. In the case of a company such as ourselves, Avaya, certain intellectual property rights and patent information about technologies that we're developing. All of these things are critical and confidential assets as well. In order to delineate exactly what those are and how much risk and value you should be associating to those assets, you really need to be talking to risk analysts. And from there, then you can start to go about documenting exactly where the information resides, who needs to see what, and from there you can start to devise your confidential data footprint. A little bit more complex because now you have to understand where those data stores are and who needs to gain access. The next thing you need to do is generate some system flowcharts. You've got people in a room, you're validating your concepts, and you get them up on a board, everyone agrees, but the next thing you do after that is once you're done with a meeting, you go out and you validate those assumptions. And that gets back to running through these previous steps. You need to run through these previous steps and make sure that what you got from the systems experts is indeed correct and valid. Once you have that, now you can identify the systems that need to be within your secure data boundary. Then you can start to build out your virtual service network architectures to support the specifics of the confidential data footprint you're dealing with. Now, when you go for the design, if you've done everything right at this point, you should have a list of the transmitting and receiving systems. You should also have an idea of how those systems are related to one another and their respective roles. You should have an understanding of the edge systems, the controllers, the users that are accessing the environment and who needs to access it. You should have some idea of the application server environment, the application, the database architecture, any exposed web services or any internal web services that are exposing for instance, for HMI type human management interface type of environments. And then finally, the data storage, consideration of methodologies, redundancies, extending the confidential data footprint to provide redundancies of storage. Remember, if you're backing something up, it's an extension of the confidential data footprint. A resulting flow diagram. You should be able to illustrate how the data moves through the network. Whether you're dealing with a linear flow or a closed loop flow. And right now, at this point, you should be able to determine that with a good degree of confidence. And then finally, you need to look at, and again, this is in dialogue with the system experts, identified, preferred, or required communication domains. And really what that means are what elements need to see and communicate with one another, and which elements need to be isolated and should not communicate directly. Once you have this information, you should be able to start to design a VSN type of implementation to support the data footprint environment. And keep in mind at step number 4, if you're dealing with those types of questions, you're probably dealing with a looped tiered automation footprint. Now that brings us to the end of part 1. By now, you should understand some of the theory involved in doing data discovery, exactly how you identify the systems that are need to be protected. And hopefully we've given you some insight as far as potential VSN designs. Obviously, I can't do an exclusive coverage all type of session because that could take hours. But I've given you an idea of the 3 major confidential data footprints that you'll be dealing with, possible combinations of how they might interact with one another. And the next thing we need to consider, obviously, once we've designed our IoT micro-segmented deployment, is how do we control access? How do we control who touches what, and how do we control the IoT devices themselves as far as what they see? That will be the subject matter of part 2. So until then, I hope you have a very pleasant day.